All right. Well, tomorrow is our Regents physics test on electricity. So we'll do what we normally do on a day before a test. I'll do a 10 slide or so review of the topics, and then I'll make sure there's a practice test posted. And I'll post the answers to the practice test as well, and you can see how you did to get ready for the test. So um, there's also the LTA that you can be working on, but let's get started with reviewing everything we've learned about current electricity and circuits. First, we learned about the notion of current, which is the rate at which charge flows. If you remember my analogy, current is like water flowing in a pipe. It's the flow of electrons inside the wire. And the equation says I equals delta Q over T. Again, I really don't like the eyes that the Smart Notebook software draws. I guess I could switch fonts. I equals delta Q over T. Current is the rate at which charge flows. So the units would be in coulombs per second, and a coulomb per second is an amp, capital A amp. And when Mrs. Rousseau, if you went on her field trip, she took you to the her circuit breaker box, which is like the fuse box. The reason we have fuses is current is really the dangerous quantity in electricity. High currents not only are harmful to the human body, they're also harmful to electrical equipment, sensitive electrical equipment. So fuses are there to make sure that if a certain current value gets exceeded, the circuit will shut down. The fuse wire will melt. Um, if the question writer doesn't give you coulombs for the delta Q, what if they give you a number of electrons? Well, your antenna need to go up at that point, and you need to do a little conversion. On the front page of the reference table, it tells you that one elementary charge is equivalent to 1.6 times 10 to the negative 19th coulombs. So you can convert to coulombs even if you're given elementary charges. And resistance, that is the opposition to the flow of electric charge, and you should know how to do the color code, and you have your Big Bird sheet, or there are color code sheets available on the internet. The three stripes that you would read, the first stripe, you just take the color and write it down, and the second stripe, you take the color and you write the number down, and the third stripe, you take the color and you add that many zeros. So the third stripe is the number of zeros. I'm terrible with this mouse. So if we had red, brown, red, the red would be a 2, the brown would be a 1, and the red would be 2 zeros. So that would be 2100 ohms. And then there's just a physics fact that you should know as a result of the Ohm's Law lab. Oh, actually, we didn't do the light bulb in the Ohm's Law lab. We did it virtually. But you should know in metals, as temperature goes up, resistance goes up. There's always a good question on any Regents physics test that asks you what happens to the resistance of a metal as temperature changes. If temperature goes down, resistance goes down. If temperature goes up, resistance goes up. All right, Ohm's law, without a doubt, the most important equation in electricity. V equals IR. Potential difference in volts equals the product of current in amps times resistance in ohms. Again, we not only use it in regular simple circuits with just a single resistor and a battery or a cell, it also gets used in series and parallel circuits. Remember, we did V1 equals I1R1, V2 equals I2R2, and so on. In an ohmic device, and that's really all we studied, we made a graph of V versus I in the Ohm's Law lab. Actually, you made two of them. And we got a nice linear / proportional graph. And the physical significance of the slope of a V versus I graph is going to be R, resistance. That would be the Y equals mx plus B. And if current is your X, that means that the resistance is your M or your slope. In an ohmic device, you get a nice straight line. Not every device has a straight line, but that's all that we investigated in our lab. Power, electrical power, is the rate at which energy is used. The rate at which energy is used. So notice that's going to be the joule per second. So power, even before we discuss the equations, is going to be a joule per second, which, as the clever title tells you, is a watt, capital W. Now we need to be careful here because that capital W, when it's a unit of measure, is a watt. You'll see a bit below the slide here that there's another W floating around. The Regents reference table gives you this three equation buffet. Power is IV equals I squared R equals V squared over R. So how do you know which one to use? Well, we write down our knowns and our unknowns, and we let that list dictate to us which equation we're going to pick. Here's where we get into trouble with the W. W, when it's a unit of measure, is watts, and it goes with power. W, when it's used as a variable, meaning out here to the left, it's electrical energy or work. If you look on your reference table off to the right where it explains the symbols, it'll say electrical energy or work. Now, all you have to do to get energy is multiply power times time, because if power is in joules per second and we multiply by time, these are going to cancel and we'll be left with just joules. So electrical energy measured in joules is power times time. So you can take this three equation sequence and do IVT, I squared RT, and V squared over R times T. All right, the resistance of a wire. This equation right here has one use. It is there to help you find the resistance of a piece of wire if it has length L, cross-sectional area A, so this area right here would be capital A. That's always measured in square meters. And this rho value, there's a table of those on your reference table, right? That's known as resistivity. And the material that it's made from determines the resistivity. So you can look up on your table. You have to be careful because on the table, one of the scientific notation values is 150 times 10 to the negative 8, not 1.5 times 10 to the negative 8. Several of you got misled by that on the LTA. When drawing circuits on your test, you should definitely use the symbols that are on the electricity page on your reference table. Before we leave this equation, we should talk about the graphs. You can graph R versus L and R versus A. R versus L and R versus cross-sectional area. Now, we already have the equation written down. Why don't you pause the video, think for a moment, and sketch out what you believe the two graphs would be for R versus L and R versus A. All right, let's switch colors. Remember, you take the two things you're plotting and you circle them in the equation. And if the x value is in the numerator and it's not squared, we know we're getting a nice straight line. And then when you plot R versus A, the A is downstairs in the denominator, and one of our 5 curve types says whenever you have something, the x value, which is A, is in the denominator, you're going to get a hyperbola. So you will have this poorly drawn with my mouse hyperbola. All right, Kirchhoff's law. If you have a junction, meaning a place where wires come together, let's do this. There's a junction right there. There's 3 different wires, and they're clipped together here. And let's say that you have 6 amps flowing into the junction and 2 amps flowing away from the junction. Let's get our units in there. And then we were to put an ammeter in here to want to know what is the current flowing in that 3rd wire. Well, Kirchhoff's law says I in, the current flowing into the junction, has to equal the current flowing out of the junction. You'll notice there was a question that looked just like this on the LTA, and there'll be one on the test as well. Here we have 6 amps in, there's the arrow, and we have 2 amps away, but we have to have 6 amps away because we have 6 amps in. which means that this meter right here would have to read 4 amps, and the direction would have to be away in order to make the math work. All right, one of our other energy units is the electron volt, and you may have to convert between electron volts and joules, and that should not be a problem because on the front page of the reference table, it tells you that 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. I know it's a very familiar looking number and we're used to a coulomb being there in electricity, but this one is indeed a joule. All right, on to series and parallel circuits. The rules are on your reference table. As long as you have those 3 series rules on your reference table, and then I had you write in between the series and parallel rules, V total equals I total REQ, V1 equals I1 R1, V2 equals I2 R2, and V3 equals I3 R3. Now those are the keys to doing series and parallel circuits because you have to use the 3 rules and then the 4 versions of Ohm's law. And you have to be patient and just try to find whatever variables that you can. So the series circuit example, because it's best if you just try an example, says draw a series circuit with the symbols on your reference table with 3 10-ohm resistors in series and a 10-volt battery. And you're going to insert meters for V2 and I total, and I'd like you to calculate the equivalent resistance and the total current. Why don't you pause the video and give that a shot. Okay, well, when you drew the circuit, you should have gotten a series circuit that looks like this. And if we want to measure V2, remember V volts across, you have to put a voltmeter around. This would measure V2. V volts across, you have to put the 2 sides of the voltmeter on the 2 sides of the resistor. Notice we didn't break the circuit. That's not how voltmeters work. And I total, we would want to put an ammeter right in the line. You would have to actually break the circuit to put in an ammeter, and that would measure I total. Now, calculating REQ, the rule says that REQ is R1 plus R2 plus R3, and we have 3 10-ohm resistors in series. So our equivalent resistance, in this case, will be 30 ohms. And now if we want to calculate the total current, I know all the currents are the same, but we don't know any of the currents. So we need to calculate, and we do that with Ohm's law. We use the I total equals V total over REQ, the equivalent or total resistance. And V total is 10 volts, and R total is, or REQ, is 30 ohms. And that would give us 10 over 30, which is 1 over 3, which would be 0.33 repeating. So 0.33 amps of current, a third of an amp. There was also a circuits wrap-up video that I made for you that talked about what is the effect on REQ and I total if you add another resistor. Why don't you pause the video for a moment and think about that? Well, if you add another resistor, our equation says the equivalent resistance is the sum of the resistors. So if you add another resistor, of course, the equivalent resistance is going to go up. And then the effect on total current, if we look up here, I total is V total over REQ. So assuming you don't change the battery potential difference or voltage, and the REQ goes up, if this goes up, the way math works, since these are inverses, the total current would go down. Hopefully you're not confused by the rule that says I total equals I1 equals I2 equals I3. Sometimes that leads people to think that you can't change the current in a series circuit. You most certainly can. But whenever you change it, everywhere you put a meter to measure I1, I2, I3, I total, they would all again be the same, but not the same as they were before. All right, we'll do the same thing, but in parallel. We have 3 10-ohm resistors and a 10-volt cell, and we're going to insert meters to measure V2 and I total and calculate REQ and I total. So why don't you take a moment and go ahead and do that. All right, when you draw the circuit, it should look something like that, except they asked for a cell. So I'll switch to red here. Oh, I was using red. And you just want the two lines, the big and the small. The four are battery. In this case, we want a cell. And we want to insert meters to measure V2 and I total. Well, V2 would be a voltmeter around the second resistor. So this will measure V2. And I total, you simply have to put the meter in the line. Remember, ammeters, this would measure potential difference. Sorry, this would measure current. This is an ammeter. And this would measure I total. I total. Now, how do we calculate REQ? This is the hardest part of series and parallel circuits, that wacky 1 over equation, which says 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over R3. So in this case, let's just do the fraction. Well, let's do our calculator. You're going to type 10 and then hit the inverse key plus 10 and hit the inverse key plus 10 and hit the inverse key. Now, when you hit enter, that's not going to be your answer, because if you look at the equation, the left side says 1 over REQ, not REQ. So after you get this, you hit the inverse button again, and it will say answer inverted. And when you hit enter, it'll give you the resistance. So when you have 3 resistors, you have to hit the inverse key 4 times, and you should be getting an equivalent resistance of 3.3 ohms. Notice you took a bunch of 10 ohm resistors, put them in parallel, and you only ended up with 3.3 ohms, because when you put things in parallel, that tends to drive the resistance down, not up the way it would be in series. So we just calculated the equivalent resistance. That's 3.3 ohms. And we now have to find the total current. Well, as usual, I total, using Ohm's law, is going to be V total over the equivalent resistance. So V total is going to be 10 volts. So 10 volts divided by 3.3, that will give us a total current of 3 amps. So I total will be 3 amps. So if you add another resistor, what effect would that have on REQ? Well, it's very tough on the brain, but the answer is if you add another resistor in parallel, it would drive the equivalent resistance down. It always does. I don't care how big or how small of a resistor you use. If you add another path, think about the cashier example. If you add another cashier, it makes getting through the store easier. If you add another resistor, it makes getting through the circuit easier. So you drive down the total resistance, which means the total current would go up. Now, if they were asking about I1, there would be no effect on I1 because, as we learned in parallel circuits, when you tinker with a given branch, it has no effect on the other branches. This is not true in series, but it's definitely true in parallel. All right, this little beauty says two identical resistors. Two identical resistors are connected in series, and they have an equivalent resistance of 20 ohms. What would be the equivalent resistance if you took the same two and put them in parallel? Why don't you take a moment to think about that? All right, well, the first thing we can do, if we have two identical resistors and they're in series, that means that each resistor has a resistance of 10 ohms. So now what would happen if you took the same two 10 ohm resistors and put them in parallel? That would look like this. Resistor and resistor, two 10 ohms. Well, on your calculator, if you do 10 inverse plus 10 inverse, and then after you hit enter, hit the inverse button again, and your calculator will say answer inverse, and you will get 5 ohms. All right, two more slides here. Unfortunately, we weren't together to do series and parallel light bulbs, but in general, when you have light bulbs in series, they're not very bright because if you look at the rule for potential difference, V total equals I1 plus I2 plus I3, it means that if you have a 6-volt battery, that each of the 3 light bulbs would each get 2 volts, so it won't be very bright. But in parallel, If you had a 6-volt battery and you had 3 bulbs in parallel, they would each get the full 6 volts, so they would be very bright. And if we were together today, I would have unscrewed one of the bulbs, and in series, you would see that the whole circuit would go out. But in parallel, you would see that unscrewing one bulb, it would make that bulb go out, but all the other bulbs would just continue on with their life as though nothing happened, because in a parallel circuit, all branches are completely independent of each other. As a matter of fact, there's our main take-home point. All branches in a parallel circuit are independent of each other. Now, if you were to have something like a series parallel combo, it's not the end of the world. You just have to um, try to collapse various parts of the circuit by using your series rule or your parallel rule. And normally you have to do the series rule once and the parallel rule once for most of these simple combination circuits. I know we haven't done these before, but let's say they all happen to be 10 ohms. If they were all 10 ohms, what would the equivalent resistance of this whole stretch be? Well, the first thing I would do is to see that those two are in parallel. And actually, on the last slide, we looked at, or 2 slides ago, we looked at what would happen if you had two 10-ohm resistors in parallel. Well, 1 over 10 plus 1 over 10, you get an answer, you invert it, you would get 5 ohms. Now, this circled piece, if it has a resistance of 5, notice this circled piece is in series with the R3, the other 10-ohm resistor, which means you would then add them together. So that would give an equivalent resistance of this entire picture if those were 3 10-ohm resistors of 15 ohms. Well, that wraps it up. I encourage you to do the practice test that I post and to get the LTA done, get your 10.3 into books, and then you should have a smooth run on the test.